In this video, I'm going to begin talking about Chapter 3, Stoichiometry. A lot of this content should be a review for you. It's going to go a little bit deeper in details of what you have gone over in previous chemistry classes, but we want to hit the high points, and we're going to try to focus on the things that you may see in terms of just the basic necessities of what you have to understand from the beginning of a stoichiometry problem to be able to work through the details and the underlying aspects of what some of the AP kind of stoichiometry problems can ask you. So one of the new aspects of the aCh exam is being able to do a type of problem or figure out a relationship of a reaction using a particulate representation. So what you have here is you have particles. You have particulate representations of what a chemical reaction or chemical equation would look like. So if you just look at this particular all these models, you don't really know what it is unless you know what each molecule is representing. And so if we kind of start with this, it does help sometimes to know what some of the spheres are representing. So if I tell you that these spheres are going to represent carbons, hydrogens, and oxygens, but you don't know which one is which, hopefully you can kind of look and see and say, okay, well, there is one black and four white spheres. And then I've got two double red spheres, and then I have a black sphere and two red spheres. And then I have a molecule that looks very similar with one red sphere and two white spheres. You may be able to kind of come up with the details of what this chemical reaction actually is. And so if I then kind of change it up and I tell you, all right, you don't know what any of these molecules are, but I'm going to tell you there are two carbons present. There are 1, 2, 3, 4, 5, 6, 7, 8. There are 8 hydrogens present, and then 1, 2, 3, 4, 5, 6, 7, 8 oxygens present. Well, from that, you should be able to determine exactly which one the carbon is. Well, we know that the two blacks are going to be the carbon. So I've got C here, and I've got C here. And that kind of narrows it down. Well, the problem is you can't really narrow it down from there because the hydrogens and the oxygens are both equal, and you don't know exactly what it's going to look like. So, is it going to be CO4? And then you're going to have two H2s plus CH2, and then HO2. Well, if you know anything about chemistry, you know that that doesn't make sense because you've seen most of these molecules before. And so what we can determine from that is that the white spheres should be your hydrogens. Now, the reason you can come to that conclusion is because actually this last molecule over here should have been kind of a giveaway. Because if you recognize that as water's molecular structure and shape, and so that should have been a dead giveaway of what this chemical formula was. So now that we know that the whites are H's, we can plug this in as this is CH4 plus, and the reds, which would give us oxygens. So I have two O2 molecules. Now let me point something out. Why is this oxygen double? Why are there two of them? Well, you should remember that anytime oxygen is in a molecular form, which means it's just with its own when its own molecule, it is a diatomic. Oxygen molecules will never, ever be by themselves. Excuse me, let me rephrase that. Oxygen atoms will never be by themselves. Oxygen always wants to make a bond with something, and it has the potential to make a bond with itself, which makes it a diatomic. Now, what I'm not referring to is for the ability for oxygen ion to be by itself. That is possible, and we will get into that much later. Now, why is this top thing that I just wrote an ion? Well, we know that ions are charged, and how did I come up with this 2 negative charge? Well, if you know anything about the charges on the periodic table, we know that group 16 gives us a 2 negative charge, which is where that comes from. Continuing with the rest of this particular model, we know carbon is black, we know oxygen is red, and so now this tells me this is CO2, and so I can tell that what that is, and then finally I have 2 water molecules. Okay, so this particular reaction gives us CH4 plus 2 O2s plus, yields. I forgot the yield symbol. My apologies. Yields carbon dioxide plus 2 water molecules. And so this is just a good way to be able to determine a particular representation of what a chemical reaction looks like. And so what we can do is we can see in a diagram of exactly why this reaction reacted in the way it did. one of the other things that I also want to bring up while I'm at this particular point is Lewis structures. I know that's something that we kind of need to focus on later on in this chapter, but I might as well go ahead and just kind of throw these things at you. Let's just see what you do remember, because these are going to be some important things. And that's the shapes, the bond angles, the polarities, the hybridization. So I'm just going to run through these, and let's just see if any of these ring a bell. The methane molecule, which is CH4, has a shape of tetrahedral. Okay. It has a bond angle of 109.5. It is nonpolar. And the IMF that would be exhibited, which is always going to be with things that are nonpolar, let me finish writing nonpolar here, is going to be an LDF, which stands for London Dispersion Force. And we're going to get a lot more in detail with how you figure these things out. And it'll make a lot more sense later on. And finally, hybridization, which is very, very, very easy. Honestly, the way I teach it is you just draw a flower petal around the molecule. Let me just kind of give you a small little example of what I'm referring to. And we're going to redraw this actually with the model that you guys are used to seeing. This is CH4. And what I was referring to is you start with a central molecule and draw a flower petal around everything that is attached, and you just label it. And so this is the S, this is 1P, this is 2P, and this is 3P, so it is SP3. And I know what you're thinking, well, why did you only put one S, and how did you come up with 3 Ps? That is something that we're going to go into detail on a lot later, but just know that there's always only one S petal. There's a potential of 3 P petals, and there's a potential of 5 D petals. And again, I know that may not make sense to you, but we will get into that a little bit later. Oxygen is really, really easy. Obviously, it's 2 molecules, so the only thing you possibly can have would be linear. Well, what is the bond angle of something that's linear? It's definitely 180. It is going to be nonpolar, and again, just like I just said a minute ago, if something is non, it automatically has to be a London Dispersion Force, or an LDF, and there is no hybridization simply because it is a dipole molecule. Okay, and then the carbon dioxide is actually the exact same as the other one because it is linear. However, there is a little bit of difference in terms of the polarity. It is nonpolar, but it does have a hybridization simply because because it's more than 2 molecules. And you don't know this yet, but we will get into it. It does actually have a double bond present between the carbons and oxygens. So if you actually draw the Lewis structure out, you would see. Did that again. You would see that there is a double bond between these two because you remember every carbon has to have 4 bonds and every oxygen needs to have 2, and these dots that I'm putting out there are supposed to be there. So just like I said a minute ago, you draw a flower petal around every central molecule, which would be here and here. And like I said, how many S petals are possible? There's only one S petal, which is there, and well, you only have one other petal left, which means it has to be a P. And finally, the last molecule shape that I want to talk about is water. And this is one you really just need to have committed to memory because you're going to see it so often. As a matter of fact, on the 2015 free response portion, there was a part where you had to draw an ion. You had to draw the water molecule surrounding an ion, which we're really going to get into chapter 4 when we talk about solutions. But this is just something important to understand how water molecules work and how they're drawn. Water is a bent shape. It is a 105-degree bond angle. It is very polar. Okay, so polar, in fact, that the IMF that it has is a hydrogen bond. Now, remember, hydrogen bonds have this a little bit different part to it. Yes, obviously it has to have hydrogen and it has to be a polar molecule, but the key part is that you have to have that bond. Now, what I mean by bond is a fluorine, an oxygen, or a nitrogen to be able to do it too. Okay, and that's kind of what that is. And then hybridization, I'm just going to show you this. Remember, water kind of looks like a Mickey Mouse shape, and it's got these 2 little lone pairs, or kind of these antennae. Just remember, all hybridization is there's one possible S there's 3 possible P's, and there are, excuse me, this is supposed to be a D, and there are 5 possible D's. And you have to just draw a flower petal around everything that is attached to the central molecule, including the lone pair. So if we just start with the oxygen, so that's a petal, that's a petal, that's a petal, and that's a petal. So if you notice, there is one S, so that takes care of that. P1, P2, and P3. So that's all that we have. So the hybridization is sp3. Okay? Here's a little video that I want you guys to just watch, and this is from Bozeman's Science, and it kind of explains the difference between a symbolic representation and a particulate representation, so you can kind of understand how some of these things could possibly show up.
Water to start with. And so what would be a symbolic representation of this phase change in water? We could look at water that's a liquid, and so the L means liquid. We're going to add a little bit of energy to that, and then we're going to create water that is a gas. And so
now, one thing that I want you to keep in mind is that this is a phase change. And what do I mean by phase change? Is that you have a liquid water going to a gaseous water. And so whenever we have phase changes, you have got to remember that these are physical changes. That's very, very, very important, because in a phase change or a physical change, it is the same product and same reactant in the same chemical state of matter, just their phase has changed. And in this case, we're going from liquid water to gaseous water. So what I want you to understand is what we've done is we've taken a water molecule that was originally had an IMF between another water molecule. Again, notice what I'm talking about. We're talking about this IMF that was established between them, and we have dissolved that IMF. But what you're left with is you are still left with water, and you are still left with water. So you're not changing anything chemically, you're just changing it physically.
In boiling water is simply water that's changed phase from a liquid to a gas. What would a particulate representation or a particulate drawing look like of that same process? We'd have water molecules here. They're now a liquid. We're adding a little bit of heat to it, and now they're a gas. And so both of those are essentially saying the same things. It's just a model so we can wrap our head around it. Let's look at hydrogen combustion. What would be a symbolic representation of that? We'd have hydrogen gas with oxygen gas. You can see that these are both gases, and then we're forming water that's a liquid, and we're releasing a huge amount of energy from that. Now, a few things you should remember, the two.
All right, so the one thing I want to point out about this is notice that you are changing. Yes, you're going from a gas to a liquid, but if you will notice, you are completely changing states of matter. You're going from a hydrogen gas and an oxygen gas to water. So this is going to be a chemical change. So there is a much greater difference in terms of what you can get chemically out of this. And notice the last one, when we were trying to take the liquid water and separate it, notice the E, and again, the E stands for energy. The energy was actually a reaction in the last one, because think about it. If you're trying to separate something, let's just talk about karate, for instance. If you're trying to break a board, you're obviously going to have to put energy into that board to get it to separate. Well, this time, we're actually combining things, and we're going to get into this a lot more in detail in thermodynamics, but when you take two chemical molecules or two chemical compounds, and you combine them to create one thing, you're going to release energy. Think about it. Whenever you have a high five with someone, you are making a contact. You are making a new chemical bond. And think about the energy that is released. It's kind of like a sound. Sound is a form of energy. And so just like whenever you make two molecules slam into each other, once they have created a new chemical compound, the energy has to be released. And this is one of those new topics that we will get into explicitly in thermodynamics, but it's something that I want you to start hearing these words and understanding them now, because energy is released. We're going to call this type of reaction exothermic. Okay, and some of you may be familiar with this term, but this is what it means. Exo means to exit or to release. So exothermic is this type of reaction.
Script means that's the number of atoms of hydrogen that we have in one hydrogen molecule. And then the 2 out front, that coefficient, is going to tell us how many molecules that we have of that. If we were to have a particulate drawing, here would be our hydrogen. So we have 1, 2, in this drawing we have 4 hydrogen molecules. So the H2.
Now, one thing I want to ask you is, how did he know that the white molecules were hydrogens, and how did he know the oxygen molecules were the red ones? That is something that you'll have to understand in terms of size differences in the atomic radii, that the hydrogen, obviously, because it only has 1 proton each, it's going to be the smallest molecule. Also, another way that you can recognize it is that if you understand the mole-to-mole ratio, which is a 2 to 1. So for every 1 oxygen, there has to be 2 hydrogens. So you should have double the amount of hydrogens. And in this case, there are 4 whites and there are 2 reds, which it's still a 2 to 1 ratio. It's just double the amount. So you can produce more than one thing. So when you have a 2 to 1 ratio of hydrogen to oxygen, you can produce 2 water molecules. Well, if we have a 4 to 2 relationship, then you should be able to produce the same amount as the hydrogen and water because they're the same mole-to-mole ratio, which gives you 4 H2Os.
Means we have 2 of the hydrogen, and then we'd have 4 of these molecules combining with 2 molecules of oxygen, and in this case we'd have 4 important. It was first developed by Antoine Lavoisier. Here he is with his wife, Marie Anne, and she...
Okay, so moving on again. So this is, again, a same kind of concept where we have a type of chemical reaction at the top. And in this case, hopefully you know this by this point, but I hope that you recognize that this is a combustion reaction. Now, again, a combustion reaction has several different types. This happens to be a hydrocarbon combustion reaction, and I want you to understand what I mean by this, because hydrocarbons are very special. Now, how do I know that this thing right here is a hydrocarbon? Well, this is kind of a common sense approach. It has a hydrogen and it has a carbon. So this is, again, a hydrocarbon. Now, the key with combustion reactions is, and I want you to think about this every time you think about combustion. Combustion, the word that always comes to my mind is boom. Now, when you think of boom, another word that probably comes to mind is explosions. Well, with most all explosions, you have to have fire. But the key to this is understanding how do you have something to produce a fire or a chemical reaction that produces an explosion. This right here is the key. Let me circle that different color, please. It is this right here. You have to have the presence of oxygen. We are all intelligent enough to know that anytime you remove the oxygen content from any type of chemical reaction, you're going to not have any type of fire, any type of flame. That is why whenever you blow on a fire, you're blowing carbon dioxide on it and the flame goes out, and you're also reducing the amount of oxygen that's surrounded by the flame. Just like whenever you, let's say you were to light a match and throw it into a bottle. Well, that match will eventually go out because all of the oxygen content or concentration that was in the bottle, the flame is going to use and to burn out. And so it will burn. It will last a few seconds, maybe to closer to a minute. But as soon as it burns out, it's done. If you were to immediately light another match and drop it down in the bottle, the flame would instantly go out because there's no oxygen content there to keep the flame going. Now, since this is a hydrocarbon, there's 2 other special things that you can note about a hydrocarbon combustion reaction, and that is the products. Anytime you have a hydrocarbon combustion reaction, the products are always going to be carbon dioxide and water. Always, always, always. Okay? And that's kind of, again, this is the same chemical representation as earlier, but now you can actually see the chemical reaction that I proposed to you earlier. One of the differences about this one particularly that I do want to point out is the fact that it was balanced. So it was 2 oxygens and 2 waters on each side. Now, there's one last thing I want to talk about combustions, and that is a tip to balance these things because sometimes they can be challenging to balance just because of the components of each side. And here's my tips to balancing combustion reactions with a hydrocarbon and a hydrocarbon only, okay? Don't always assume that just because it doesn't have a hydrocarbon, it's not combustion. Anything mixed with oxygen can be a combustion reaction, okay? So here's the tip. So tip number 1 is double the HC. Now, obviously, hopefully you understand what HC means. That stands for hydrocarbon. So what you essentially do is you just put a 2 in front of the hydrocarbon. And the next step is balance as needed. And the third and most important step, so again, balance as needed. And the third and final step is very, very crucial because if you don't do this step, you're going to get it wrong, is to reduce coefficients if needed. Again, if you don't reduce the coefficients, let's just pretend in this particular case, if we did it the way that I just have it, so let me actually erase some of this, so make it a little bit easier to see. It's actually not going to work, so I'm just going to write over it in red. If we did it with a 2 right here, this would actually end up coming out to be 4. This would come out to be 4, and this would come out to be, excuse me, let me retract that. the carbon dioxide would come out to be 2, and the water would come out to be 4 as well. So what am I getting at? If you notice all of these numbers, the 2, the 4, the 2, and the 4. So again, hopefully that makes a whole lot of sense in terms of what you see in the mole to mole ratio and how you can determine the coefficients of each one of these reactions. This is another type of reaction, and this actually shows a picture of what's going on. This is actually burning a magnesium ribbon. And if you notice something, it gives off an enormous amount of light. In fact, if you burn one of these things and you stare at it long enough, it can actually burn your retina. You can actually go blind from this type of reaction. And so if you'll notice in this picture, what they have is an actual particulate representation of a piece of magnesium. And then obviously we know that oxygen is in the air floating around us. And when you light this on fire, this is a type of combustion reaction. And I know what you're thinking, well, isn't that a lot different from what you told us earlier about the hydrocarbon? Yes, it is different. However, you still have the combination of oxygen to produce some type of oxide as a product. I know what you're thinking, what is the oxide of the previous reaction? If you go back and look, carbon dioxide is going to be your oxide product. And if you notice what happens is you have these two these two molecules come together and form magnesium oxide. And just one thing I want to point out is that if you notice that every magnesium is a 2+ charge because it's in group 2. And then every oxygen is a 2 negative charge because it is in group 16. And so they do form a 1-to-1 ratio. And so for every 1 magnesium, and you can recognize this from the chemical equation, you have 1 magnesium, you have 1 oxygen. Okay, and then obviously the 2's are there to balance it out. And the other little thing I want to point out is where is this little 2 coming from right here? It's because oxygen is one of your diatomics. Okay, so just make sure that you understand that. Some other example of some combination reactions. This one right here is a very, very, very important one. The second one, and you are going to have to know this if you don't already know this. This is called the Haber-Bosch process. You have to know this process. This is the combination of nitrogen gas and hydrogen gas to form ammonia. Okay, again, this is the production of ammonia. And if you don't know what ammonia is, and go to your cleaning products in your household and you will definitely find ammonia on there. Again, this is a very, very, very important one we're going to spend a lot of time talking about. And then obviously the bottom one, you have one thing plus another thing yielding something that is an entire molecular compound. Okay, I've got a little video I want to show you now.
We will pour our magnesium into our flask. Chemical reaction occurs, we slide it under there, we lower the test tube down, we make sure there's an airspace at the bottom, and we begin collecting the gas. Now you can see a chemical reaction occurring here. It's actually producing heat. You can feel the warmth. And this is what's going on when we described our reaction. The magnesium is combining with the hydrochloric acid to form hydrogen gas, which is floating up, and magnesium chloride, which is dissolved in the solution. Now, once the reaction is done, that's when the fizzing stops. We will then test to see if hydrogen gas actually was produced. So we're basically testing your ability to carry out a chemical reaction. Okay.
Now, one of the things I want to kind of interject right here is how would you know if a chemical reaction actually occurred and how hydrogen gas was produced? Remember, one of the 5 signs of a chemical reaction occurring is bubbles. And so that is one of the things that you can see occurring here. And the other one is evolution of heat and light. Well, obviously, there's no light being given off, but as he said in the video, there is some heat. It is extremely exothermic, which means heat is released and it is getting extremely hot. And the last one is if a gas is given off, well, we know it's bubbling. Well, we want to know what type of gas that is. Well, he just asked if hydrogen gas is one of the products. And there is one way to test. I'm going to let you finish watching the video to see what way it's testable.
So, looks to me like our fizzing has stopped. You can see some condensation up here from the heat, some of the water vapor that was present. The hydrochloric acid is dissolved in water vapor. It was there. So what you'll do now is you very, very carefully slide your test tube up so we can get access to it. We slide it up about that high. Now notice, We are not in any way, shape, or form touching the test tube or allowing it to turn over. If that would turn over, then the gas would escape. All right, then we just kind of slide that to the...
Now let me ask you this question. Why would the hydrogen gas not naturally escape if it were hydrogen gas? Well, you got to think about this. What makes air rise above the other? Well, it's just like fluids. Density is going to be your key indicator there. Hydrogen gas is less dense than atmospheric gas. And when I say atmospheric gas, yes, I'm talking about the nitrogen, the oxygen, and any other gas that you can come up with that would be in the atmospheric air. And so hydrogen naturally is going to rise above atmospheric gas, and so it's not going to come out of the bottom of the tube because the atmospheric gas is keeping it from coming out.
And now we do the standard test for hydrogen gas, and this is where I come in. When you think you're ready, I will come around and I will very simply say, okay, you ready to test for hydrogen to see if you produced it? And you'll say, yes, I am. So we will have you hold a splint. We will light a wooden splint. Remember, fire burns up, so we hold it like that so that it gets a good flame going. And then you will very quickly put it up in the test tube, and what will happen is we'll get a miniature explosion. Now, what you heard was a squeaking, whistling noise. Now, when the Hindenburg, the famous dirigible or blimp, exploded right around the time of World War I, just before it, what happened was it was full of hydrogen gas because it was so light it held it up. It exploded, so multiply that teeny explosion by about 1 million, and you'll get what happened. Now,
So I hope this gives you a really good indication in terms of how a chemical reaction occurs and a visual evidence of two different ways that a chemical reaction occurred. Number one, that the magnesium ribbon was dissolved in the hydrochloric acid because of the production of bubbles, and two, the production of hydrogen gas as a product due to the flame test. Okay, so that's just an interesting way to look at it. Here again is a decomposition reaction. Again, these are just the basic types of reactions that we're looking at. The way you can tell it's decomposition is very simple. Is something has to break down. Something has to turn into two or more substances. Well, if you look, let's look and see if we can tell what type of reaction this is. Hopefully you can recognize now that we have water and it is decomposing. Now, again, is this a physical change or a chemical change? This must be a chemical change because this thing is chemically different from what it began as. Water is literally being destroyed. Now, there is a name for the process of this reaction, and I do want you to know this process because without it, water cannot be decomposed. It is called electrolysis. And the way that you have electrolysis is by taking two metal rods, connecting it to a power source such as a 9-volt battery, and sticking them down into the water, and it will begin to bubble. You can actually perform this on your own. If you take a 9-volt battery, imagine a very, very miniature sized jumper cables that you would connect to car batteries, but they're called alligator clips. And if you could just connect one to each positive and negative terminal of the 9-volt battery, connect it to pencil lead. That's all you need. It's a conductor of electricity, and if you'll take those two pencil leads and you stick them down in the water will begin to bubble. Now, when the water begins to bubble, you know that a gas has to be formed, and it is not water gas. It's not water vapor, okay? It is actually producing two different states of matter, two different molecules. And if you think about it, if you look at the two colors, what you're going to get is you're going to get H2 plus O2. So water is going to split down into its molecular form. And obviously it's not balanced. You've got two water molecules and you've got two hydrogen molecules. Now it is balanced, and that is the electrolysis of water. And so here you have some other examples. The first two are very important, and I do want to make mention of what these are, and I would like for you to write them down. This first one is called a metal carbonate, and I really need you to understand what a metal carbonate decomposes into, because this is going to be something you're going to see a whole lot of. And the second one is a metal chlorate, and you do need to know these two special types. A metal chlorate. And then we're going to look at the product. So metal carbonates will decompose into metal oxides and carbon dioxide. So from this, you can deduce what the products are going to be. Now, specifically in the metal carbonate, calcium is the metal, and so if it's a metal oxide, and again, make sure that whenever you write your new compounds that you do check your charges. So you're going to have Ca2 plus, O2 minus. So if you notice the 2's will cancel, so you have CaO, and then obviously carbon dioxide is going to be CO2. This one happens to do work out to be balanced, okay? But again, the key here is making sure that you understand that if it's ever a metal carbonate, and you have to recognize that CO3 is going to be a carbonate, does deduce into a metal oxide and carbon dioxide. Okay, next we have a metal chlorate and a metal chlorate, and I'm going to write this beneath it. Metal chlorates decompose into metal chlorides and or plus oxygen gas. So in this case, you're going to get the metal, which is potassium, with chloride. Now remember, ide by yourself, so it's just going to be Cl. But remember, check your charges. K is a group 1, so it's plus 1. Chloride is a group 17, so it's minus 1. So you're going to get KCl plus O2. And this is not balanced, so you would, of course, have to go through and balance this and figure out exactly what it is. And again, your 2, 3, 6 rule kind of kicks in. What am I talking about here? If you've got 3 here and you've got 2 here, let me change the color. It's a little bit hard to see there. If you've got 3 here and you've got 2 here, well, the lowest common multiple between the two is going to be 3. Or excuse me, 6. My apologies. And so there's already the 2 there. So if you have a 3, give it a 2. If you have a 2, give it a 3, and that makes 6. And then you have the 2 potassiums and 2 chlorines that you also have to balance, okay? And so again, this other one, this sodium nitrite, is also going to be decomposition, but I'm just going to kind of move on from this. All right, again, this is a combustion reaction. Now, again, I've already talked about this. Now, if you'll notice, both of these right here are the hydrocarbons. And so anytime you have a hydrocarbon combustion reaction, the products are going to be the exact same. CO2 plus H2O for both of these reactions, okay? Again, these are generally rapid reactions that produce a flame. Most often involve hydrocarbons reacting with oxygen. This is the key right here. If you don't have oxygen, you can't have it. And I've already mentioned this once, but I'm going to just write them again. There are tips to balancing this. So the tip, all right, tip number 1 is double the HC, and what I mean by HC is the hydrocarbon. Step 2 is balance as needed. And then the last one is 3, which is reduce if you can. And again, those are the tips in order to balance all of these. So I do want you to try to balance these. Just kind of give you some practice of exactly what to do. So again, like I said, I'm not going to run through all of these, but the tip is to just double these first 2 and then balance as you would need. Obviously, you've got a 5 and you've got a 2 there, and you may need to go back and reduce those. Those aren't always going to be given right there, so you're going to have to figure out what those are as well. Okay, this is kind of shifting gears a little bit. This right here is the most used. So in saying that this is the most used step, I cannot overemphasize how important that understanding how this step is used, because if you can't go from grams to moles, you're not going to be able to do anything in this class, because it is the quintessential part of what chemistry is, because so many times we're given things in grams and so many times we have to convert them to moles, or vice versa. If we're giving moles and we need grams. And so the ability to understand how this particular concept works is extremely crucial to your success in this class. Now, I know in honors chemistry we did go to atoms or molecules a lot. That has been cut down in terms of the types of questions that are asked using atoms or molecules. Avogadro's number is very important, but it's rare to the connection of a lot of the topics in terms of mathematical application. It does still pose an important aspect in some of the topics, but the actual calculations of atoms to molecules is reduced in this class. But again, Your ability to be able to go from grams or moles is the most important thing in this entire class. So I do want to make sure that you can understand how to accomplish those goals. First, what the heck is a mole? Again, basically it's a way to count. It's just simplifying. It's making something that's really big really small. So the mole is really another way to think about it. It's just a ratio. So if I ask you what is 1 dozen, well, you would say, well, that's 12. Well, if I ask you what 1 gross is, that's 144 things, and it can be anything. I mean, it can be pennies, it can be pencils, it can be whatever in terms of counting is used. Like 1 ream of paper. Some of you know that that is 500 sheets of paper. So instead of having to say, oh, well, go get me 1,000 sheets of paper. Well, that's a little bit difficult for some people to comprehend, but if you say go get me 2 reams, people know that, hey, I need to go grab 2 of those big, thick things of sheets of paper. And so that is how we can understand this. So 1 mole was just an easier way to say a really, really large number. And that number is 6.02 times 10 to the 23rd atoms. So again, that is essentially what a mole is, and it's nothing more complicated than that. It's just making it a huge, large number, or in some cases a really, really small number, into an easier way to express it or identify it. And the standard for the mole and where it comes from is there are exactly 12 grams of carbon-12 in 1 mole of carbon-12. So what we're trying to get at is, and what I'm trying to get you to see, is that if you have exactly 1 mole of carbon-12. Again, now carbon-12, what does carbon-12 mean? That means you have 6 protons and you have 6 neutrons. Well, why is that important? Because remember that this number right here is the mass number, and the mass number is the number of protons plus the number of neutrons. Well, how do you get 12? Well, because carbon definitely has 6 protons because it's the number 6 on the periodic table, and so 12 minus 6 is 6. That tells me there are 6 neutrons. So if I have 1 mole of carbon-12, it's going to have this many atoms. It's going to have Avogadro's number's worth of atoms, 6.02 times 10 to the 23rd atoms. But that amount of atoms is going to weigh exactly 12 grams. So this was the standard of how everything was built around. All right, so I've got a little small video I'd like to
destroys gardens. And some of you might be thinking that it's a growth on your ant's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amedeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists look at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Unfortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You'd really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is... anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole. Avogadro.
So again, I hope that kind of gives you a clear understanding of exactly what a mole is. And go back to that whole idea of about if you received a mole of pennies the day you were born, you could spend $1 million a second until you were 100 years old, and you would still have 99.99% of that mole of pennies left. If that doesn't tell you an understanding of how large this number is, then I don't know what will. But again, I think that's just a great little video of representing of exactly what a mole is. Okay, again, this is Avogadro's number, kind of as the video talked about. And this is not the greatest looking man in the world. It's kind of funny. I do think he actually looks like a mole, so it's weird that it's called the mole. And then the last part of this video is basically just one simple conversion. And so what we're trying to go to is we're trying to go from 122 grams of sodium, and we're going to try to figure out how many moles of sodium that is. And so it's a one-step unit cancellation. And remember, there's something that's always important. If you have mole in parentheses, and I want to add a little disclaimer, if it's with grams or atoms. Now, we should know by this point something about the mole-to-mole ratio, and that's a little different. We're talking about when moles is in parentheses with grams or atoms, it's always going to be 1, and then if it's with grams, it's going to come from the periodic table. Now, remember, if I give you a compound like Na2O, well, obviously there's not one box that contains Na2 on the periodic table, so you're going to have to find the molar mass of this thing, but that's a little different. So just let's run through this real quick. Hopefully this is very simple. So we're going to start with 122 grams of Na, and I'm actually going to kind of shortcut the way I used to do it, and I'm just going to show you the simpler way. We're just going to do times and a line. Hopefully that by this point you should be able to understand how to do all this. And remember, every single time you set up a unit cancellation, you have to include the unit and you have to include the compound you are working with. Because if you don't, number one, for my purposes, it is incorrect because I don't know what you're going from and what you're going to. And number two, it actually helps establish a procedural part of converting from one thing to another. So again, 122 grams. Now let me ask you a question. Why did I put grams on the bottom? Well, if you understand anything about a math concept, you know for units to cancel, they have to be in a divisional process. So in this case, grams are going to cancel, which leaves me with moles on top, which is exactly what I wanted. And now I need to plug some numbers in. So just as we have up here in the very first, remember, if a mole was in parentheses, and again, parentheses is kind of the old way we used to do it, with grams or atoms, which it is, it will be a 1. And then if you look at the grams is in parentheses, it comes from the periodic table. Well, there is one box with Na on it, and the molar mass, again, always round to 2 decimal places in molar mass, and so it is going to be 22.99. So now mathematically, what we've now got to determine what to do. Do we multiply, add, divide, subtract? Hopefully you know that you do have to divide at this point, and so the final answer will be 5.31 moles of Na. And the last thing that I do want to point out is make sure that whenever you do these things, that you maintain significant figures. Back up here in the given, there are 3 significant figures, and we maintain 3 significant figures also in our answer.